Hello students, today we'll go to the next point, that is a power IGBT. So in the previous classes we have discussed that is a MOSFET and BJT, and now we are moving to the IGBT. So what is a power IGBT and meaning of this and working and structure of this? So now we'll see here, I have shown a total 3 symbols. So in this one, power IGBT is at the right side here. This is a symbol of the power IGBT, and we have already gone through the MOSFET. This is a symbol of the MOSFET, and this is a BJT. And what is IGBT and how it is created? So IGBT stands for insulated gate bipolar transistor. So insulated gate bipolar transistor is the largest device in power electronics. The gate circuit of MOSFET and collector emitter circuits of BJT are combined together to form a new device. This is called as a IGBT. What we have did here, we have made the combinations of these both, the MOSFET and BJT, and using the help of these two symbols we are created a IGBT. So this is a new symbol which is having again terminals like MOSFET and BJT. 3 terminals we are having. Now what are those 3 terminals? One is a gate and collector and emitter. Compare the MOSFET and BJT. Which one we have taken? The names of these 3 terminals. The gate is taken from the MOSFET, and the collector emitter of the BJT has been taken. We also call emitter as a source, collector as a drain for this IGBT. Now the IGBT has a structure. In how the structures can be designed with the help of the MOSFET, we can go through. So now we will go to the structure of the power IGBT. So before moving that structure, we'll just see how to turn on and turn off this power IGBT. So how to make this IGBT turn on. So I'll simply say, when the voltage is applied between gate and emitter. So when you are going to apply the voltage between here, I'll show this and this. So when the voltage is applied between gate and emitter, the IGBT is said to be turn on. So the current flows from the collector to emitter. So when you will make the turn on of this power IGBT with the help of 2 terminals, that is a gate and emitter, the current will start flowing from collector to emitter. So now the current flows from the collector to emitter, and the negligible current flows from gate to emitter when the gate emitter voltage is removed, and the power IGBT is going to be turned off. So suppose consider, when you are going to remove the connection of the voltage between the gate and emitter, the collector to emitter current is also going to be stops. So this is nothing but it is makes the power IGBT off. So now we'll go to the structure of this. Now look at this diagram. This is a structure of power IGBT. So what you can see on this diagram? So number of layers are how much, and number of junctions are how much? The number of layers are, so 1 2 3 4 5 5 layers are there, and the junctions are how much? See here, these are the junctions: 1 2 3 4 4 junctions are there. So where you are going to make the 3 terminals connections which you are seen in the symbol, where these 3 terminals can be appeared on this structure. So I will show you the gate which we have seen in the previous symbol. That gate is connected to here. So the emitter at the center, here there is a terminal, and the collector is here. So now these are the 3 terminals. Gate is again connected to the N plus layer, and it is not directly connected. There will be a silicon dioxide material is acting as an insulator, so it is kept between the gate and your N plus layer. So that is a gate connection to the N plus layer. And collector side, we are seeing one P plus extra layer, that is called as an injecting layer. This injecting layer is created, and N plus, that is a buffer layer. This is an extra is used, and remaining what we have seen, that already we have seen in the previous structure like a MOSFET, that is a drift layer, and this is a one body layer and N plus layer. So NPN, so NPN along with drift layer, it is also included. It is just like a simple diagram as like a MOSFET. The extra one is added, that is a injecting layer P plus, and you already know what is a plus and minus, that is indicating the doping intensity also we can say. So here what is happened, the P plus injecting layer and the N plus regions are heavily doped with the doping intensity of 10 raised to 19 per centimeter cube. The P type body region is moderately doped. So you are observing here P is a without any plus and minus symbol. So that layer is called as a moderately doped with a doping intensity of 10 raised to 16 per centimeter cube. And N minus drift region is lightly doped. So you know minus is indicating the lightly doped, doping intensity of 10 raised to 14 per centimeter cube. And next, the N plus buffer layer, what you are seeing here, that is called as a buffer layer. Some of the IGBTs are consisting this N plus buffer layer and some are not. The N plus buffer layer is not necessary for the operation of IGBT. Usually they take it or leave it. The IGBTs with the N plus buffer layer are called as a there is a one word we can use, that is a punch through, PT IGBTs. The IGBTs with N plus buffer layer, I am telling. Here you are having the buffer layer, N plus is there. So this type of structure of the IGBT is called as a PT, punch through. This is actually asymmetric. It is having a asymmetric voltage blocking capabilities. So it is nothing but if you are having the N plus buffer layer, the IGBTs have faster turn off times. So for that purpose only we are using this. So when you are going to make turn off of this IGBT, you can immediately turn off when you are having the buffer layer. If it is not there, then it is not possible to turn off your IGBTs immediately. So what happens if you are using the buffer layer and you have created the structure? This type of IGBTs can be used in a chopper and inverter circuits. And when if you are not using this buffer layer, so that type of structures of IGBTs can be used for the rectifier type of applications. So this is structure of the explanations of the your power IGBT. And this is a last point of our power IGBT, that is a VI characteristics of power IGBT. See the graph. So what are the lines or curves are indicating here? Again, also we are going to observe the voltage and the current characteristics of this power IGBT. So where you are going to apply the voltage and from where to where the current starts flowing in the structure and in the symbol of the power IGBT, we are observing in this. So here the characteristics is plotted from we can say collector current ID. So where you are observing this is here. The collector current ID is here. This ID indicating the drain current, or we can also mention it is a collector current. You write any one, so both are same. So in the symbol we are shown it is a collector, and also we can take it as a drain. Mention any one, ID or IC. And similarly here the voltage you are going to apply across drain and source, or we can say it is a voltage across emitter and collector. So both are same. So the voltage and current measurement can be done. Voltage across the emitter and collector, and current it is from the collector, we are observing in the graph. Now what happens when you are going to give the voltage and we are going to observe the current? So which type of which controlling knob or controlling terminal you are using to check the variations of the collector current, whether it is increasing or whether it decreasing? So we need voltage which is called as a gate to source. So gate to source, or we can say it is a gate to emitter. So this gate to emitter voltage, gate to source, it is a controlling voltage. So when the voltage that is VGS, we can see, so here they are shown VGS, VGS4, VGS3, VGS2 and VGS1. So these are called as a controlling gate to source voltages when VGS is greater than VGS threshold. So threshold means it is a minimum voltage required to make the IGBT on. So when your VGS controlling voltage is greater than the VGS threshold, your IGBT will be turned on. So the IGBT will be turned off if the voltage VGS is less than VGS threshold voltage. So I can show you there is a one region of on and there is a region of off. When the current from the IGBT, that is IC, will be off, your VGS is less than your threshold voltage of VGS, and when the IGBT is going to turn on, your VGS is greater than threshold voltage of VGS. The on and off regions, it is represented in the graph. And the next one, BVDSS, is here you can observe BVDSS is a breakdown drain to source voltage. Above the BVDSS voltage, if you are going to give the voltage, the IGBT will be damaged. So now this is a similar diagram of the MOSFET. So how we are going to increase the IC current? So how you are going to increase the VGS? VGS1, if it is smaller initially, if you will get the this is a curve. When VGS2 you are increasing the voltage, controlling voltage lightly more than the VGS1, then you are getting a second curve like this. Current is going to be increased, Similarly, VGS3 and VGS4, when the voltage you are going to increase, so your current is also going to be increased and becoming the constant like this. So this is indicating how you are going to control the flow of the current, how you are going to increase the value of the current, you are going to decrease the value of current. It depends upon totally controlling voltage, that is a VGS. So this is nothing but explanation about the your VI characteristics of power IGBT. So